Hi, this is Mark Weitzman. Welcome back to my channel on YouTube, Theoretical Physics with Mark Weitzman. Today I want to do an exercise from the Feynman Lectures on Physics, 21.9, and it's an interference problem, basically, from Chapter 29 of the Volume 1. I left that out over here. Volume 1 of the Feynman Lectures on Physics. And I'll show you the problem right now. So this is the problem. It's a long word problem, but it's an interesting problem, not difficult at all. A field engineer testing radiation patterns is flying in a helicopter at a ground speed of 120 miles an hour at low altitude in a circular pattern of a 2-mile radius, about the midpoint between two vertical dipole transmitting antenna that lie in a north-south line. For the frequency being used for the test, the antennae are a half wavelength apart. Normally the antennae are operated in phase. However, the transmitter operator decided to play a joke on the field engineer by changing the phase relation between the antenna at such a rate that no change in radiation intensity could be observed aboard the helicopter. If he started this change when the helicopter was due east of the antenna, at what rate d alpha dt was he changing the phase relation when the helicopter was 30 theta degrees north of east of the antenna? So let's just draw a picture. Sorry. We have go back to the iPad. We have a helicopter flying in a circle, and so this is the let's say this is the XY direction. This is the XY plane, and the dipoles are coming out of the plane, and they're separated in the north-south direction by a half a wavelength. And the radius that the helicopter is flying in the circle is going at this velocity in a circle. This is 2 miles. I apologize for the use of English units in this problem. Remember, these problems were given to Caltech students in 1962, so the U.S. was like, and a lot of physics was like far from metric at that time. So we'll just have to use these units for now. It will cancel out in the end. And the velocity is 120 miles per hour. And so let's just calculate the phase difference. Remember, we don't need the full, we're in the radiation zone. We'll assume that 2 miles is much bigger than a half a wavelength. And we're in the radiation zone, and so we don't have to worry about the full formula for electromagnetic fields and everything. We just know that it varies as 1 over r, and in this problem, since the radius is constant at 2 miles, we don't have to worry about that. There's some various factors of epsilon naught c squared we don't have to worry about. And since the dipoles are in the z direction, we'll always have a perpendicular, the line of sight of the antenna relative to the observation point will always be perpendicular, so we don't need the sine theta factor will always be 1. So everything really works out easy. It's just pure interference here. So let's calculate the phase difference, and to do that, again, I'll draw another diagram. This is lambda over 2, and so this is one dipole, theta, and this is a perpendicular here, and then we're going to go, and this distance is what we're interested in. This is the extra distance x. This is also theta. So sine theta is equal to x over lambda over 2, or x is equal to the distance is lambda over 2 sine theta. And the phase difference, phi, that this causes is kx, or 2 pi over lambda, times lambda over 2. That didn't work. X is a lambda over 2 sine theta. So 2 pi over lambda times lambda over 2 sine theta is equal to pi sine theta. So that's useful to know. I'll box that equation. Now, if we didn't have to worry about the trick in the problem with the engineers changing the phase difference, we would know that so instead of it being that, the actual value of phi is going to be equal to pi sine theta plus alpha. Alpha is what we need to know. And the intensity from two waves is proportional to the absolute value of, the first wave we can consider as 1, and then the other one is shifted by a phase difference, e to the I phi. I don't want to confuse, okay, absolute value squared, which is equal to the absolute value of 1 plus cosine phi plus I sine phi, absolute value squared, is equal to 1 plus cosine phi squared plus sine phi squared, and this is just equal to 2 times 1 plus cosine phi. So that simplifies nicely. So we can write the intensity I. Let's say the original intensity of one dipole is I0, 2 I0, 1 plus cosine phi, which is equal to 2 I0, 1 plus cosine. Now we substitute what phi is in, pi sine theta plus alpha. Okay, so this is what our intensity is. And our intensity is constant, which implies that pi sine theta, plus alpha is constant. So differentiating this, we get pi cosine theta d theta dt. It's supposed to erase it and it doesn't. Pi cosine theta d theta dt plus d alpha dt equals 0. So this is basically solves our problem. D alpha dt is equal to minus pi cosine theta d theta dt. Now we know that d theta dt, which is the same thing as omega, which is equal to v over r, which is equal to 120 miles per hour divided by 2 miles. So this is equal to 60 per hour, or let's turn that into legitimate units, 1 over 60 radians per second. So that's what d theta dt is equal to. So we substitute that, we get the alpha dt is equal to minus pi cosine theta divided by 60, and this is in radians per second. And now let's just multiply that by, to get it in hertz, we'll multiply that by 1 cycle over 2 pi radians. So this is equal to minus cosine theta over 120 cycles per second. And so finally we have d alpha dt is equal to minus cosine theta over 120 hertz. And that's our answer. So that's a cute little problem. It's a type of problem where, you know, average physics students or average engineering students probably get in trouble for saying this, but the average student is going to look at that as a word problem, and he's going to have problems. He's going to have problems translating it from English to mathematics. He's going to think it's a much more involved problem than it is. But actually, it's just a very simple, basic interference problem. And as you can see, the solution is very short. So the good physics students, the A physics students, they keep their head about them and they read it, and then they say, okay, let me read it again slowly and draw a diagram and put the data on there and figure it out. Oh, it's really easy. I just have the phase, and the phase is somehow constant instead of varying. Anyway, I just wanted to show you an interesting problem from the Feynman lectures on physics. I hope you'll join me next time for some further problems. Bye-bye.